Hello and welcome back to the Resources Conservation and Recycling webinar program. It's wonderful to have everyone with us today. My name is Mitchell Jones. I'm the Outreach Editor at Resources Conservation and Recycling. And we're joined today by Satinder and Sarra. We're very, very privileged to have them both with us today. And we'll get to their presentation in just a moment. A few brief notes before we get to that. So this is the English language version of the Resources Conservation and Recycling webinar program. We also offer a Chinese language version of the program. So if you have Chinese language skills and you're interested in those programs, be sure to check those out. This particular program runs every second Thursday at 10 a.m. Pacific time. Now, this program is scoped to match the journal, Resources Conservation and Recycling. So you can expect to see presentations from all elements of the scope in this program. We try to run a very balanced program where we afford equal weighting to the various scope categories. So as I say, you can expect to really see a broad range of different topics covered in this program or these events. The one thing that we do ask for is that authors or presenters afford some consideration to audience accessibility. We want this program to benefit as many people in our community, in our research community, as possible. And what that means is that we encourage them to refrain from using too much jargon, too much subject-specific terminology, and to provide some contextual and background information to their research area that everyone can appreciate before they dive into the specific details of their study. This program is registered, so register only. You need to register with this program. You can find the registration links in the Resources Conservation and Recycling newsletter, which is circulated at the end of each month. You can also find those links on the social media pages. So if you go to X or Facebook or LinkedIn and you go to the Resources Conservation and Recycling page, you will find the links there. Or you can also find them on the Elsevier Journal homepage for Resources Conservation and Recycling. You just need to visit the About tab and visit the webinar calendar there. You'll find a full list of all the upcoming webinars in addition to all of the previous webinars, which are archived to YouTube for everyone that wants to view them after the event. You can find them also directly by visiting the YouTube page, youtube.com/@RCR Journal. You'll find all of the archived content there. You can also find the live stream for this. We're currently in the Zoom environment right now, but this is also live streamed to YouTube. You can watch this live on YouTube as well if you prefer to not register for the event through Zoom. The final point is this program that we run, these webinars, it's really for you. It's for our research community. It's for your benefit. And we want these webinars to be useful to you. So we very much encourage any feedback. We are very flexible in changing elements of the program. If you have comments, compliments, criticism, things that could be improved, things that shouldn't change, be sure to tell us. You will find a survey will open when you leave the webinar today, and you're very welcome to drop any feedback you have in there. It's just a series of multiple choice questions. Won't take you more than a couple of minutes. There's also the opportunity there to leave more detailed feedback in the text box if you prefer. Okay, so I will then bring up the formal program for today. So that I can kick things off officially. So we've had our welcome address. I'm going to now provide a formal introduction to the journal, a formal introduction to our speakers for today, a couple of notes on housekeeping, followed by our presentation, 20 minutes, approximately 20 minutes from our two speakers, followed by question time, and then some information about the next event and closing remarks. So hopefully everyone is already familiar with the journal Resources Conservation and Recycling. It's an Elsevier journal. I like to say that it's quite clear, I think, at least, or obvious what the research interests of our journal is or are. The name, Resources Conservation and Recycling. We're interested in all aspects of resources conservation and recycling. Some specific scope points to target systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. If you have any top quality research in those areas, be sure to send it our way. Couple of housekeeping notes before we start. If we could please have all communication in English. We are very, very blessed to have an audience and also speakers from a very, very wide range of backgrounds and countries. But for the purposes of today, we do need to be all able to understand and communicate with each other. So if you could please use English. We have closed captions available, and they're currently running in Zoom and also on YouTube. If you, for example, English is maybe not your first language, and you would benefit from some captions, or perhaps you prefer to watch your webinars with the captions on the train or something like that without any audio, feel very free to use them. They are there for you if you would like them. Post any questions that you have over the course of the presentation or at the end of the presentation in the Q&A, which you'll find in your toolbar. We're also very happy to facilitate more direct verbal expression of your questions or your open discussion with our speakers. If you would like to speak directly with Satinder or Sarra or both, and you would like to ask them something or talk to them, either with your microphone or with your camera and microphone combination, then just indicate you're interested in doing that using the raised hand reaction in your toolbar, and we'll be more than happy to activate your camera and microphone so that you're able to speak directly with Satinder and Sarra. So, introducing our speakers for today, we are very fortunate to have Sarra MAGDOULI from the University of Ottawa in Canada, and Satinder BRAR, who I'm going to introduce on the next slide. They are speaking on the topic of when biotechnology meets critical elements chain supply. Dr. Sarra MAGDOULI is an assistant professor at the Department of Civil Engineering at the University of Ottawa in Canada. Dr. MAGDOULI has gained strong academic and consulting experience. She is an expert in management of emergent contaminants and bioconversion of residues for the production of high value added products. She also specializes in treatment and management of industrial waste, contaminated mine and industrial water, polluted soil, mine tailings, contaminated treated wood, and various types of industrial waste. Finally, she works on the bioxidation and bioleaching processes for the extraction and recovery of metallic values from primary and secondary resources. Dr. MAGDOULI has a deep technical and business understanding of the mining industry and its sustainability challenges. She also has an excellent track record in student training and research paper publishing. A very warm welcome to Sarra. I will now introduce Satinder BRAR from York University in Canada, who will be joining Sarra and commencing with the presentation after this slide. Professor Satinder BRAR is the James and Joanne Love Chair in Environmental Engineering and Director of One Water Institute at York University. She works in the converging fields of value addition of wastes and sustainable removal of contaminants. She has received several national and international awards and honours, notable ones being in 2025, Ministry of Ontario Innovation Award for Stakeholder Engagement, in 2021, Best Paper Award, and in 2019, Eddy Principles Processes Wastewater Medal winner. And in 2017, she was awarded the Grand Prize in University Research for Excellence in Environmental Engineering and Science by the American Academy of Environmental Engineers and Scientists. She leads the bioprocessing and nanoenzyme formulation facility at York University, has published more than 400 articles, edited 12 books, and at least 55 invited talks to her credit. It's my absolute pleasure to invite both Sarra and Satinder to the floor for their presentation. Thank you so much for being with us today, and I believe that Satinder will begin the presentation.
Yeah, thank you so much, Michelle, for the warm welcome and the introduction. So just sharing my slides. Let me know which mode do you see. You see the presentation mode?
Yes, looks good.
Okay, thank you so much. So, well, I have with me Dr. Magdouli here. So myself and Dr. Magdouli, we will be discussing today's topic on biotechnology, meeting critical minerals chain supply. We have been already introduced, so I don't need to introduce, us again. And so let's move on to the general introduction on the topic. Sorry, what is biotechnology? Because we are talking about, biotechnology's role in critical minerals, it becomes important to understand what it is. Everybody knows that as the term goes, it applies science and technology in relation to the living organisms, and henceforth, whatever products and models that are derived from them, which could be, for the purpose of developing knowledge or even in the industry and different services. And of course, there are a wide range of applications all the way from health, veterinary sciences to agricultural fields and even environmental biotechnology. And specifically, deriving from biotechnology, I would say what are critical minerals? Their definition is a little bit clouded in the sense that there is no standard definition of a critical mineral. It is more country specific, and the criticality is more dependent on supply versus demand, and of course, as well as the societal needs. If we look at the criteria, which is on which we derive the significance of these critical minerals, is actually related to their domestic supply or basis, and what is the global demand for these critical minerals. So I'm just mentioning a few countries and European Union here. So US, European Union, Japan, and Korea, they have deemed certain minerals and metals as critical based on certain criteria. And these criteria are that either they should have a high degree of import reliance, that is, there should not be any break in the supply. They should have relatively fewer or even no substitutes, is subject of geopolitical risk as well. We see that, every day almost now in the media, and also has a high level of concentration when we talk in terms of production. This is very critical. And now in Canada, because myself and Dr. Magdouli, we are here in Canada. So specifically from the Canadian perspective, I would say there is a list of 34 minerals. They are considered to be critical. So we have the rare earth elements: aluminum, titanium, magnesium, manganese, vanadium, chromium, zinc, nickel. These are the ones that have been considered as critical by the government of Canada. And of course, critical minerals, why they are essential? Because they are building blocks for the clean and digital economy. And their application is, widespread, leading to clean power generation, all the way to zero emission vehicles. And we talk a lot about advanced manufacturing, 4.0, and so on in space and defense. So that also, includes critical minerals. And for decades, if we have to talk in terms of the presence or exploitation of these critical minerals, so China has pursued a strategy to control the rare earth elements production, processing, and advanced manufacturing. And this has subsequently led to China being the leading producer and processor of minerals. If you would see here, in the images shown below, so all the way from mining to the high-end rare earth elements, we have China that is, ruling the roost. Canada is also progressing towards, the use or exploitation and processing of these critical minerals. But our processing is limited, or the use or application is limited up to the magnet point of view. We are still not at the stage when we are developing some components there. So moving on from critical minerals, now let's go to the specifics of rare earth elements. Why are they important? Because they are, you can say, a specific category under the list of critical minerals. Rare earth elements, actually, they comprise a group of almost 17 chemical elements, as you see here in the periodic table. So we have scandium, yttrium, and the whole lanthanide family sitting here. And if we look at the right figure, where we are trying to represent the distribution of rare earth demand in end user applications, this is in the year 2021, you would see that, it is all the way from batteries to catalysts to ceramics to glass, magnets, and metallurgy, and it is a widespread distribution of these rare earth elements. So that's why we would say that they are important. And most importantly, I would say if you look at these numbers in terms of their demand, it was $6.8 billion in 2021, and there will be an increase in this demand, and the increase in demand projection is claimed at $12 billion by 2026. So almost a doubling in just 5 years in terms of the demand for these rare earth elements. And of course, if we talk about their estimated global rare earth market from 22 to 23, if you can see, 32, sorry, you can see it's almost exponential. You have the market value here in USD million on the y-axis, and the years from 22 to 2032. So almost in 10 years, there's an exponential increase. And if we look at the application categories, you would see most of them are applied in magnets, and then the metal alloys and catalysts, and there are other applications all the way from polishing to pigments, which also take a chunk of the pie in terms of the applications. Now let's look at the reserves of rare earth elements. So definitely we discussed already in the introduction that China has been developing these resources for a long time. So China is the leading country in terms of global reserves. And then we have Vietnam, Brazil, Russia, India, and of course we also have Canada to some extent here. And then if we go at the production scale, likewise, China matches its global reserve in terms of production. But then United States is next in line in terms of production. And then Australia, Myanmar, and Thailand, they follow in terms of the trend in production. Now, rare earth elements, they could be extracted, of course, using several means, and mostly chemical means, physical and chemical means are the ones that are employed. But here we wanted to bring to your knowledge the challenges and drivers in biomining, because biomining is not used to that extent, but it is coming up as an interesting strategy to extract these rare earth elements. So the traditional methods, as I was explaining earlier, have been normally pyrometallurgy and hydrometallurgy. However, they have not been found to be eco-friendly, posing several environmental challenges. And of course, there is lot of energy input which is required in these processes. There is dust generation, so air pollution is there, and of course there are also greenhouse gas emissions that's happening, and which is sort of, you can say, creating challenges if we continue using these traditional methods. So does biotechnology offer a solution? Yes, biotechnology could be considered as a valuable solution here, and that solution would be coming in terms of bioleaching. Now, bioleaching, specifically speaking, what it does is you are using certain microorganisms. I'm just giving one example here, Acidithiobacillus ferroxidans, okay? And so as you have the term thio there, that means it's related to the sulfur, and then we have the bacillus strain, and ferroxidans, of course, there is a relation with iron. That's why you see the ferroxidans here. And this microorganism has been known to dissolve and recover metals from various complex matrices, including even the mine tailings. And microbial activity is not something new. It has been all around us. It is all around us even now in terms of natural biogeochemical cycles that we see, be it the carbon cycle, the iron, sulfur, and even in the mineral resource solubilization. And microbial degradation of the sulfuric matrix from rocks is also something which has been happening. and is happening around us. So you can see here on the right-hand side, this picture, just to show you that even in the 17th century records, they should describe the occurrence of copper-bearing waters at Rio Tinto in Canada. And if you would like to consider this as a first natural bioleaching operation. And of course, microbial degradation of the sulfidic matrix, what it does in the end is it produces sulfuric acid. And then because there is production of sulfuric acid, there is release or solubilization of these metals in the acidic media, which makes it then easier to recover them. Now, continuing on with the challenges and the driving forces in biomining, it has been mostly that the ore grades have now declined. There is a depletion of easily mined deposits. And of course, even natural microbes are becoming limited. There is, of course, we see day by day an increasing demand for critical elements. There is waste accumulation happening due to the mining industry and environmental impacts, related to that waste accumulation. And of course, there is a push from the linear economy to the circular economy. So we want to get there. And the way we can get there is biomining could provide one of the ways or paths to achieve, circular mining. And of course, there has been a trend in biomining now from moving from natural to engineered microorganisms, which can work more efficiently in order to solubilize and extract these metals. And of course, there is also an interest now moving from the base metals, because bioleaching was initially restricted to the base metals, moving on to the rare earth elements. So in all, what I mean to say is that circular economy, if it encompasses bioleaching as one of its elements, then that could, strengthen the circular economy, which is actually the path forward when we talk about critical minerals or rare earth elements. And if we talk about biomining specifically, so for example, the primary ores that are considered here are monazite and xenotime, derived from, and then there are the secondary sources such as the fly ash, the red mud, the phosphogypsum, even the circuits, the waste electrical and electronic equipment. So bioleaching has been traditionally successfully employed in extracting these valuable metals, that is, such as gold and copper, from the printed circuits. However, it is still to be exploited fully to its capacity, I would say, for the recovery of rare earth elements in mine tailings. So that would be, I think, something interesting to see in the time to come in the mining industry, as the mining industry is moving towards biomining. So at this point, I would move on to my colleague, Dr. McDouley, who is going to dive into the specifics of biomining and give you some examples from our research that we are conducting in our group. Go ahead.
Yeah, thank you, Professor Brar. So moving and adding to what have been said already about the primary and secondary resource for securing rare earth from waste and especially tailing, they represent a valuable option for extracting of those rare elements. So we have seen that tailing contain worth metals that are valuable to more than hundreds million. And one of the research that we are conducting right now with the Professor Brar are extracting those element and strategic element from oil sand tailing as added to other tailing from copper smelting that contain also valuable rare earth element. And the good advantage of those tailing, they have already been crushed and they could be processed easily with bacteria without needing any reprocessing or crushing or any pre-treatment that could enhance or facilitate the reaction or the addition of microbe to the surface of those mineral presented in tailing. So coming with the lower treatment process of those tailing in comparison with the primary ore that contain valuable and base metal copper or gold, we have seen that the processing of those ore could reach to 60% of the total process. So from that perspective, tailing could be a valuable option, especially to lower those costs, because they have been already processed. In between those tailing, also they are having a big problem in terms of disposal and liability. So the cost for those management of this tailing could reach a higher cost, but also a higher environmental impact and footprint. So the need of bioleaching or biotechnology to extract and recover those rare earth elements from tailing it could be a sustainable and valuable and renewable option for environmental and society. And we need all to bring economic, technology, and environment, as well institution and legislation policy to work on this. We have seen, as Professor Brar have been already talking, many driver and many barrier to extract those metals, especially with coming to the conventional method. But we see the need, especially with what's happening right now in terms of securing those metals. But again, there is also a driver that we could go and secure those metals from secondary waste, especially those tailing. Please, next slide. So what we need to optimize for tailing valorization and rare earth element recovery to enhance the circular economy, especially in the mining of those elements from waste. So there is a big chain that we need to think about the upstream as well the downstream and purification step to reach to that level. Please, next slide. One of them is securing a good and potential candidate of microbe or acidophile microbe or fungi that are well known for extracting those metals. And you have seen in the picture, so for many of our research, we always target extremophile condition to secure those extremophile strain for example, and then we need to make some culture as well, study the metagenomic and metabolic of those strains. And this approach is also applicable to rare earth leaching experiment that we are conducting now, where we have been selecting some microbe from the tailing itself and from extremophile location that we have been carrying for other projects. So in the picture also, our work previously have been selecting some strain, and we have seen a good potential. You can see our publication from acid mine drainage, and we have been using those strain for copper, but also for gold, and we are potentially looking to use them for the earth element extraction due to their high acidophilic potential. Next slide, please. So here, a publication that has been already published in RCR journal with our PhD student, Kati Jussi. So we see many industrial wastes that have been already listed by Professor Brar. So rare earth element, they could be secured from primary as well secondary resource like phosphogypsum, red mud, electronic waste, as well crushing catalysts. So many strain could be used for extracting those rare elements as well scandium or yttrium from different waste, including using of some acidophilic bacteria, thermophilic, moderate, or extremophile bacteria that could survive till 80 degrees Celsius. So some of microbes have been already tested for rare earth, like Aspergillus niger, that could reach up to 74% of extraction of rare earth. And red mud, also we have been using some bacillus and some acetobacter, where the leaching rate of some scandium and lanthanide and yttrium could exceed 50% of the extraction. Noting also some fly ash coal that we could use fungi producing oxalic acid responsible for solubilization of organic acid. And still work is ongoing, and we are actually working in our group with some of those strains, mainly glycanobacter, that we are also trying to use it for rare earth element because of their ability to produce glyconic acid that is adding to solubilization of rare earth elements. Some publication will be coming soon for this extraction method through bioleaching. Next slide. So how microbe, after we select our microbe, after we know our location from where we select, and we should conduct our experiment enrichment as well culture, and to arrive to that we need also some fundamental background. Although bioleaching, as already said by Professor Brar, has been known, and we know the ability of those acidophilic bacteria to produce sulfuric acid through the reaction of oxidation of ferrous to ferric ion, as well the sulfur oxidation to sulfate that is responsible for the producing of sulfuric acid. So this sulfuric acid is responsible for solubilization of those rare elements. This is the direct mechanism that added to this mechanism, we have also seen another mechanism which is direct, that is also enhanced by organic acid production. So those microbes, they can produce organic acid responsible for the complexation and acidolysis of rare earth element that could be chelated as well, complexed with those acids to enhance solubilization, but also to avoid any reprecipitation in the media. And here we can see the EPS role and the biosurfactant and chelating agent that could be produced by those microbes when they are releasing organic acid and enhancing the reaction with an earth element. Next slide. In this figure also, we see another model. So we have been talking about the direct and indirect mechanisms through the last slides. But again, here we are conceptualizing the same process for bioleaching from monazite, which could already listed before as primary resource for earth element. And for that, we return to the same process that is enhancing contact bioleaching. So we see the monazite. So microbe could be attached to the surface of the mineral through extra polymeric substance to enhance the reaction of rare earth complexation with organic acid production. This is the contact bioleaching. Otherwise, for the non-contact bioleaching, so we have here the production direct of organic acid, where we don't have a direct contact within the membrane, but we could see the complexation and the chelation of rare earth 3+ plus oxalic acid complex that also are contributing to maximize the efficiency of rare earth elements solubilization during the process. Those two mechanisms already exist when we talk about rare earth element solubilization, but also we could find both of them, especially the cooperative bioleaching. So we have the both contact and no contact. They are contributing to rare earth element solubilization during the bioleaching process. Next slide, please. Same here. So after prospecting, after understanding the fundamental theory and fundamental principle for bioleaching, some of recent and emergent trends are trying to maximize the recovery while targeting the effector or the efficient actor for solubilization. Here, the example of some acidophilic. So we could enhance the recovery of and extraction and solubilization of those elements through acting on the acid tolerance. So we see here that there is so I cannot put my... Okay, there is here the mechanism of the H proton that are responsible for the acidolysis of earth element when they are encountered to the cell. And then we have the mechanism B, that is the metal tolerance. So we know all that when we are extracting metal, we have also some toxic compound like metal, heavy metal, cadmium, arsenic that are responsible to inhibit the process of bioleaching and of our microbes. So we can play around for those metal tolerance gene, like PPX or protein polyphosphate, that they are responsible for the maintaining the buffering, but also maintaining the inhibiting the effect of those toxic compounds and those metal. Another mechanism that we can also play and engineer is the heat tolerance. So we could work on protein like similar to heat shock protein and to tolerate high temperature. Especially we know our microbe and our acidophile, they can reach to temperature around 80 degree to enhance the bioleaching reaction. So from that, maintaining a good temperature could be engineered through heat action through HSP protein, but also other protein like and DNA repair system and some other protein and enzyme that we could engineer for increasing the efficiency for rare earth element solubilization. Last, also the tolerance of high salinity. It is also another mechanism to be engineered, like tyrellose protein or some other vitamin. So those are kind of protein that they allow for our acidophile high tolerance to the salt, especially if we're gonna extract our rare earth element from a salty media like brine or any waste stream that high TDS and high salinity. From that perspective, we can conclude that engineer and synthetic biology could be also an option to increase the efficiency, and many works are undergoing to increase this efficiency through rare earth element bioleaching. Next slide, please. Some of the work that has been already listed in the publication of RCR that we can use CRISPR-Cas technology for increasing the efficiency as already tested when acting on heat or salt or osmotic pressure, as well temperature tolerance. Meanwhile, also the expression of some protein like RAS protein could be helping in the increasing of ferric iron production and then increasing the overall performance of biomining and bioleaching of rare earth element. Other also potential mechanism is the overexpression of EPS, extrapolymeric substance, to enhance the direct bioleaching and the contact between the bacteria and the mineral matrix. And those could regulate the biofilm formation as well increase the bioleaching efficiency. We have actually some work that has been already done and published through studying the role of EPS for the extraction of gold, and we have been also optimizing the media as well, the sugar and polymonosaccharide for the EPS production without genetic engineering, although it could rest as an option to look for, but we can also optimize the media to enhance the production of EPS, and we have seen a good result, especially in the gold recovery, and you can check our publication in this field. Meanwhile, as I already mentioned, the resistance of heavy metal like cadmium, copper, zinc, that they could inhibit our process. We could also improve the resistance by some overexpression of some specific pump to maintain those elements not toxic for our bacteria. Last slide. So when after finishing with the microbe and engineering and then understanding the media, we need now to work on the design and which option we're gonna use it for our reaction. Is it a CSTR reactor or heap leaching through some column? Here we need to choose depending on the percentage of the load, depending on the criteria that we have set, but also depending on many criteria that we will see later. So which option we could choose to make our experiment, but also later on for the scale up at industrial scale. Both have advantage and disadvantage, and depending on many parameters, the choice is crucial. Next slide. So here the heap designing leaching that could be applicable to rare earth element, although there's a lot of work that has been done on heap leaching for the extraction and the bio-oxidation of gold, copper, as well base metal. So it's similar and typical process that we need to follow up. especially for the extraction of rare earth element. For the tailing, the treatment of or the pre-processing of the ore is not required, but if we are working with monazite ore, we need some reprocessing, like crushing or grinding before enhancing the bioleaching. This step is not present in the tailing if we will enhance the heap bioleaching. After that, we put our tailing in the reaction with our microbe that we already selected or we already engineer, and we optimize the media. And then we, through some percolation and optimization of parameter like aeration rate, circulation rate, as well temperature and pH, we could could efficiently control the bioleaching. Following that, we are generating a solution of rare earth element that could be neutralized and then precipitated to have rare earth element solubilized, but also precipitated in the form of oxalate rare earth element that could be commercialized and purified later. And with that, we generate also some effluent like acid, because we have already produced sulfuric acid through the reaction that they need to be treated before discharge to the environment, as well some solid that they need to be filtered before returning back to the site for management. Next slide. So here we have seen that to optimize the heap leaching, we need to also to run those experimental design and parameter for enhancing or efficiency, controlling the bioleaching, and those is coming through lab tests and bench scale tests and semi-pilot tests. Those figures are presenting one of the processes that we have already optimized for gold recovery and some for copper also as well. So we have also some publication that we did this work based on some enzyme as actor to enhance the biooxidation through enhancing the glucose oxidase production, but also use other model of catalase. If you are interested, I could give more detail with you as well. You can also check our publication, and we'll be happy to respond later if you have some question related to this process. So before piloting scale, we need to pass through many steps similar for bioreactor or CSTR and agitated mode. So for those, we know that we need to optimize the dissolved oxygen, the solid load, the high metal contained the solution, the device of agitation, and the reactor design to enhance the mass transfer and the oxygen transfer and the homogeneity of pulp. Although what we have seen right now in our current experiment, there is some slow kinetic, and we need more process control and more scale up in terms of scaling up our current work for our earth element. Next slide. So not only upstream is crucial to optimize the rare earth element, so we need the fundamental knowledge, we need also the downstream part for recovery and purification. Many technologies are already listed here that are responsible for the purification of rare earth element like solvent extraction, precipitation, to have our complex of rare earth element that could go to the market. There's other technology that we could use it like dialysis, but also electrodialysis, and some membrane also could be used like ceramic membrane or hollow fiber membrane that could help in the separation and the purification of rare earth element and the removal of impurity before being in the market. As well, we can use also biotechnology and engineer some biosorbent like microalgae or some lignocellulosic adsorbent that we also could help in the recovery of rare earth element. And here there is a lot of emerging trend in this field. So I invite you, if you are interested, to check. There is a lot of work that has been done, and we're already focusing on some of those options for our recovery of other metal that could be applicable for rare earth elements. So next slide. Finally, takeaway lesson from today: bioleaching although it has been already a valuable option to treat material in the past. Like we talk about 50 years that we know about bioleaching, that they are already contributing to more than 20% of the global demand of copper and 5% of the global demand of gold. So we see here the potential of bioleaching as the available option. However, for our earth element, there is behind some work to be done for upstream as well downstream, especially for if we are applying this technology or this option on waste like tailings. Application of bioleaching is expanding now for our earth element. Some publication, we see it from the last 10 years, and more work are emerging for this field, especially with other emerging technology to use some biocatalysts, some engineered microbes, some CRISPR-Cas technology, as we see. And all of this taken together is more to optimize the process, to increase efficiency, to decrease cost, and increase revenue and profitability that we can later scale up and have some interest from technology provider, but also mining company, and then policy and regulator to use this technology for our waste that they have been left for a long time and they are being considered as waste and not a valuable or profit that we could get it from them. Finally, to take a lesson from today, biotechnology, we have seen it support really the critical element here. We have seen copper, cobalt, nickel, zinc, and now the door is open for our earth element to support circular economy, but also the critical mineral chain supply that every country and is looking to secure their element for their digital economy and their manufacturing, but also for electrical vehicle. With engineering technology and emerging technology, we have seen also some potential for using artificial intelligence. We have some publication in this regard for optimizing gold recovery when using ANN and other tools, and that could be a good option for the next to optimize the bioprocess. And some of the work that is currently undergoing under net gravity condition, which is opening new door for space biomining. Some of the work is already conducted in Australia in this field, and we can target space as a new valuable resource for recovering those elements and those lanthanide or what we have been reported in the literature. So here we come to the end. Thank you so much for your attention, and I will leave the floor for you, Mitchell, and Professor Brar, if you have more to add on this. Thank you again, and happy to answer to your question.
Thank you so much, Satinder and Sarah, for your wonderful presentation. I have to say that you did absolutely beautifully with your introductory content in terms of background and context. That was wonderful. Sometimes that doesn't happen as much, and you guys did a really great job with that, so thank you. So I'm going to convey that the floor is now open for questions. If anyone has questions they would like to ask, and I see that one's come up in the chat already, but I'm going to leave that for a moment because I have a couple of points of my own to start us off. So I wanted to ask you guys, and this kind of ties into that, the first aspect of your presentation. So what is the sort of, I mean, this is maybe a little bit of an abstract question, but what's the sort of current share of overall mining industry that actually utilizes biotechnology? Is biotechnology actually used in practice currently in mining, and how widely?
You want to go first? Sarah, go ahead.
Yeah, I could answer that question. Thanks.
Yeah,
So,
go ahead.
yes, bioleaching is actually right now applicable for some country like Chile and Finland. As I did mention during the presentation, we are using biotechnology last 50 years to recover 15% to 20% of copper and 5% of gold globally. And we have seen many pilot technology already on site, like Finland or Chile or South Africa, that they are very efficient for the recovery of similar metal, but also nickel and zinc and cobalt also. Still, work is not done on rare earth element if we return back to say, but I think that will be another avenue for the future to secure those metals. There's a lot of work to be done before reaching to that level of biooxidation or bioleaching experience with gold and copper and other metal. Yes.
So just to complement, Michelle, what Dr. Magdouli stated, so 5 to 10% of some of the base metals are being recovered actively using biotechnology currently in the sector.
That's wonderful. That's and that's very nicely. Numbers are always helpful in this sort of thing, aren't they? So the next thing I wanted to mention was, I mean, you spoke about primarily it seemed about bioleaching, but you did also have this slide where you looked at the entire process chain from extraction to the processing to and you had the different countries there. I sort of wondered which elements of this. So, I mean, you talked about bioleaching, which I suppose is around the ore extraction, but I sort of wondered if you could comment on the various parts of this process chain that are most well suited to biotechnology and what could be implemented in terms of biotechnology in that part of the process chain. What comes to my mind initially is, although I haven't heard much about the bioleaching aspect, this ore extraction aspect using biotechnology, what I have heard about is so-called phytomining and micromining, whereby you essentially use hyperaccumulated plants or fungi to up-concentrate or scavenge for low concentrated rare earth elements or metals or whatever that are scattered in soil or in stone or whatever else. And that would be perhaps an example of biotechnology that sits more to the left in your process chain at the extraction kind of perspective. So I just wondered if maybe you could think a little bit about the process chain, the different elements in it, and maybe comment on which are well suited to biotechnology and what biotechnology could be used in those parts of that process chain.
Okay. Maybe I can start and Sarah can then complement. Okay, so biotechnology certainly at the ore stage, it can be used for extraction. We already, as Dr. Magdouli stated, that it has been used for base metals so far, just that it has not been applied in rare earth elements. So that's something which is being done, and even for the waste side of it has been done, like in the in the electrical circuit boards, or even in the electronic equipment, if you want to say. It has been successful bioleaching in order to extract those base metals. And that is the upstream part then, in terms of if you're talking about the process flow. And then, of course, we have the downstream processing. So Dr. Magdouli, while she was presenting that section, she did show there is a scope for, biosorption. So biosorption is something which could be applied for rare earth elements as well. So I think, Sarah, you can maybe add on to this, how biosorption can actually, be used in downstream processing.
Yeah, sure. And yes, I totally agree with you. The upstream part will be a good place to target to apply biotechnology, as well downstream through some adsorbent that they are coming from some waste lignocellulosic adsorbent that could be tested. Also, so there is a potential to use algae as adsorbent for those elements. I could say that at the end of the day, biotechnology or bioleaching will not bring a solution for the extraction or the purification of earth, but it could contribute to some extent, to some part and some percentage, to help in the extraction and the recovery process. We will not replace the hydrometallurgy or pyrometallurgy or whatever we have as chemical leaching or a worldwide process that they are using, but we could start to extract at some level or some percentage those metals through microbial action. And if we could at least target 10 to 20%, that is very good and enormous value, but not in total abolishing or declining the chemical leaching or the hydrometallurgy pathway for extraction of those metals.
So is there then some kind of logical or attractive, I mean, obviously you said it's going to supplement it. Is there some specific divide that you see as being logical in where you would keep your traditional processes and where you would implement biotechnology?
That's a good question.
Yes, that's a good question. Right now I don't have the answer. This answer should come through a techno-economic analysis and as well environmental and social analysis to be done before any project or before starting any case study for the application of bioleaching. There's many driver, many many barrier and many need that they have to be put in consideration. Life cycle also to be considered if we apply biotechnology in this field. So there's a lot of input to be optimized and study to be done before taking the decision to apply a bio process. Telling that hydrometallurgy will continue to be used as valuable and option to recover. And as I did mention before, if we target to some percentage to ameliorate our current situation and to bring some innovation, and we show through some pilot scaling study, and also we conduct our life assessment and environmental work before, that could be big. I think science will be a good achievement for science, but also for our research in the future for those elements.
As Sarah spoke, so something came into my mind, if probably bioleaching, this is again a thought process. I don't know if that could be done. Let's say if there is a mining industry which is located in a highly ecologically sensitive zone, so there bioleaching could be, I think, more appropriate, and should be used rather. Let's call it should be made mandatory, So that way they don't have to follow up with all those, cleanup processes which accompany the regular traditional approaches. So I think that is biomining could be relevant under such specific situations, example. And then of course, techno-economic plays an important role, as she mentioned. So, are you looking at high value metal or, something which is large volume and low cost, or is it high value and low volume? So this all, I think, changes the equation.
I think those are some great answers to some tricky problems. And actually, it's quite interesting. We had a webinar. I think was it the last one or the one before that was also on mining, and there was some mention. I can't remember. It was in one of the American states, but I can't remember which one. But I think it was Nevada, and they were basically saying that actually from a logical perspective, it was not a very sensible place to mine. I can't remember the reason. It might have been the concentration of the resources there, or the energy costs, or the water. I don't remember, but it wasn't really a good place to mine. But it basically was a place that it was easy to mine from a legislative perspective. And of course, as you just said, Satinder, that's where some of this stuff comes into it. For example, if it was an ecological zone and you had certain legislation that you needed to comply with, then maybe this would be, makes a lot of sense. So then maybe the next question would be, do we have any indication, or I don't know, has someone done the sort of maths or the assessments? What is the comparable sustainability of these biotech processes compared to the original ones, in terms of if we have any like percentage numbers, in terms of like percentage reduction on key eco indicators or something like that?
You meant like life cycle analysis of bioleaching versus
whatever is most appropriate to meet the point, I suppose.
I think there are some life cycle analysis studies that have been reported on this biomining versus the traditional mining techniques in terms of comparison. There you have these ecological indicators like greenhouse gases or even the toxicity to aquatic life and all that. So, but as we were discussing, and as Dr. Magdouli, when she went through the slides, she later on she explained, biomining has not been exploited to that extent in rare earth elements. So you would not come across, if we are specifically mentioning rare earth elements here, we don't have any such, comprehensive studies which have reported those indicators. But if we go to the base metals, yes, studies have been done and they have reported that bioleaching is definitely more sustainable option. Okay. But sustainability doesn't mean that it would be an economical option. Okay. There are two different factors totally. So then you need to get into the cost benefit analysis and all that. Okay. So, but yes, coming back to the answer to your question, yes, for base metals, it has been reported to be sustainable.
Okay, one final quick question before I switch to the few audience questions that we have. So when we're talking about biotechnology, obviously we have options with, plants, bacteria, fungi. Where do you see the potential in terms of the spectrum of organisms available? Is it in a specific kingdom or depends on the case? Do you have some insights?
Sarah, you want to go? Go ahead.
Yeah, I can go. Yes, actually, the selection or the bioprospecting of those microbe or fungi, depending on the mineralogical and physicochemical property of the ore or the waste that you like to extract, and some of the waste could be adaptable more to fungi because they are excellent producer of some organic acid, like taking example Aspergillus niger or some other fungus that they could produce those organic acid and be actor for rare earth element solubilization. That could be option for other if some bacillus or some glyconobacter or other acidophilic bacteria could be also option for bioleaching if we have a direct contact with the ore, and this also coming through some analysis to be done before the choice of the microbe. So we need to screen well our microbe, we need to optimize well our culture media operating condition, but also we need to understand the competition or the dynamic of interaction between indigenous microbe that are already existing in those wastes. So there's a lot of factor and a lot of study to be done in this perspective to select the best choice, and not only from biotechnology perspective, but also from efficiency. Fungi could take more time and we need to produce acid, then we need to go to the other step of bioleaching, although for the other bacteria, it could be through direct process. And this, here we enter for another consideration, which is the time and the cost energy consideration for this process, as well also the mineralogical content or mineralogical property. Some bacteria or some fungi depend on their tolerance to salt, depend on their tolerance to the heat, to the heavy metal presence in the media, as well to the pH. Those conditions, sure, they will play around a big role for the selection of our microbe to be heterotrophic, to be autotrophic, to be moderated, extremophile, to be thermophilic, or whatever we have. That lot of criteria and lot of experiment to be done before the choice of the best microbe to enhance our reaction.
Okay. Sorry,
Just
Satinder.
to supplement, Michelle, phytoextraction, because you mentioned plants as well. So phytoextraction is pretty slow, and normally it is not used so far. in bioleaching to that extent at all. It might be at research stage, but mostly it's bacteria, like Dr. Magdouli mentioned. So
I can
Thank you,
also add on
Satinder.
that,
Oh,
if you are using plants, that's another second problem, because what you're going to do with the plant, phytomining
Exactly.
after you extract, so it will be another problem of managing those waste products after you have get your metal extracted. So let's bring another level of complexity, but it could be a valuable option for bioremediation plants and biodegradation of some compound. Extraction is behind some work to be done.
very nice. Thank you, Sarah. 3 quick questions from the audience here. So the first one I'll just read off. So I think this is a bit more of a question directed at your research groups. But anyway, any opportunity for PhDs for LMIC students or research support to PhD in LMIC focusing on mine waste pollution and health risks associated with artisanal and small-scale gold mining in Kenya and Senegal?
Okay. Is it in terms of current opportunities, or is it in opportunities in general, or is it so if the question can have a bit of context, then I think it would be easier to answer.
Okay,
Or
well,
I give all the text and answer.
well, if you like a sentence each.
Okay. So currently, I would say like current is for me is in time scale of 3 to 4 months. I don't think it's possible, but moving forward, like along with Dr. Magdouli, because we collaborate together on this research. So probably, let's say next year around summer, the answer could be yes. And down the line, over a year, yes. So I don't know if I answered the question as required.
I'm sure you did very well. Thank you. The next question, why are some elements more difficult to bioleach than others?
Wow. I think that needs us, what I should say, a course, like we deliver these undergrad courses. So probably it's a lot of things because each element has different chemical characteristics, different properties, different oxidation states. So it's the chemical part of the element, and then combined with that comes the alignment of bioleaching. You need those specific microorganisms which can solubilize through the organic acids these specific elements. So there are many things here, the element itself and its relation to the microorganism that we are dealing with.
And then another question here, do you see potential in implementing bioleaching using filamentous fungi for biogenic organic production as well as for selective mTOL extraction, such as oxalic acid production for gallium recovery or REE precipitation?
Sarah. Go ahead, Sarah.
Yes, there is always a hope. There is always a potential in this area. Fungus or fungi are very known for oxalic acid production, and many literature has been reporting this potential, especially for oxalic acid. And I have seen that for gallium, you can check the literature, but through our experiment, yes, we have been optimizing oxalic acid, glyconic acid, citric acid, and we have seen good improvement for yttrium, for gallium, and for other metal. Yes, and we are using for that some organic acid producing microbe. That could be also some fungus. Similar to that, I can add, we had also been working on using Aspergillus niger and some fungus for the production of some enzyme like glucose oxidase that also help in the bioleaching field. And that fungus, I think they have a role or big role to play here for our earth element because they are potential producer of many bioproducts useful in biotechnology perspective of bioleaching.
We're starting to run a little over time, but I just quickly, we've got another question here. Bioleaching process needs days for getting maximum efficiency. Have you worked large scale using intensified reactors?
We haven't done it so far, but it is doable. You can accelerate bioleaching, okay? And you can, like I think Dr. Magdouli did show one of our setups where we had used enzymes, for example. So enzyme is next step. You're already, you've crossed the production of organic acid and the enzyme. So you can accelerate it by going to the product directly rather than growing the microorganism and making the entire process, slower. So it is possible. This is one of the ways. And then people also use hybrid approaches, chemical and bioleaching together. So chemical is just to trigger and then bioleaching takes over, So yes, it is feasible.
Very nice. The final question that I always like to leave for last from my side, I like to give our presenters always a chance to provide a call to action, perspective on the future. So just as a prompt for you, what do you see shifting? What do you see stuck? What's at stake? What needs to happen? Core challenges for this in the field of academia and in industry.
Okay. So maybe I can answer academia and Sarah goes industry way. Okay. Given her, because she has been in consulting before with the mining industry. So, okay, academia way, I would say that the challenges that we have at present is, optimizing, let's say, the bioleaching process for several elements together. Okay. And then if we are talking about the waste, we did mention some examples, but mine tailings, etc., then I think the matrix complexity becomes a big challenge. Okay, but when you're working at a very small scale in the lab, it's fine. But if you want to translate those results to the next stage, getting it to the pilot scale and finally the field application, I think you need to think about it early on, how to manage that so that the results would be easily translated. And then, of course, scouting through different kind of microorganisms. I just mentioned when somebody posed a question, how does bioleaching, what is the type of element does it affect the bioleaching? So it's, flipping that response in a different way that as the elements change, so do the microorganisms. So we need to scout for more microorganisms. So that sort of in a time scale, increases the time and hence the delay. Moving on to the industry side, Sarah.
Yeah, I can also add on the academic part is, there's a lot of work ongoing for bioleaching and those application here. I think one of the major barrier is like everyone is working slow individually. There's no that's kind of collaboration through academic field and through researcher in this field. So that's one of the part. And again, the scale up of the process in the lab need to be more. There's not a lot of work to be done, and the funding would be another idea. We didn't touch that, but funding is also one of the thing barrier. We need more industrial, more aware about this application and more about the advantage. So there's a culture and educational culture about the application to the industry that we can use this biotechnology approach for extracting those metals. And that's from an industry perspective. I think some awareness, some education should happen, and this should come from academic as well also regulation and policy through having some stream for funding for this approaches. I can say the major drawback I see also for the industry is the cost. So everyone or every industry need to get their process fast and how they're impacting their economy or their entire budget. And this need to be considered by them. So for them, cost is a big parameter to be considered in their application. So there is some work to be done, especially for life cycle assessment, as we did mention, but also cost benefit analysis to be presented to the industry. And that for that reason, we need more work from academic researcher. We need more proof of concept. We need more semi-pilot, and we need many effort to reach to that level for scaling up and getting industry supporting those technology. So yeah, there's a lot of work.
Lucky that you guys are there then, I suppose. Thank you both so much for such a wonderful presentation. I will have to end us there because we have had a very long session today, but a very interesting one. So again, thank you so much to both of you for your wonderful presentations. I would normally bring up my screen now and provide the information for the next event and the closing remarks. But we have a few administrative changes with the program. So due to the popularity of the webinars, we will actually be expanding the program to include a new format called Research Conversations, which will be a panel-style discussion of 3 to 4 panelists on a single topic. So that will complement rather than replace the existing webinars. So I will not provide you today with additional details, but that will be coming soon. So stay tuned for that. Thank you again so much, Satinder. Thank you so much, Sarah, for your wonderful insights. I really, really enjoyed hearing your, this is such an interesting area. Thank you so much again.
Thank you so much for the invitation, by the way. Thank you so much to
Thank you,
RCR
Mitchell,
as well.
and thank you for RCR. Thank you so much.
It's our pleasure. It's our pleasure. Thank you for being with us today.
Thank you.
Okay, then I'll wish everybody a good day, a good night, good morning, depending on where you are in the world. And we'll see